Okay, starting with the caveat again that I am not really an expert on artificial intelligence, machine learning, and so on, but I am a user. So I've been using it to basically produce early warnings for agriculture, flooding, and some diseases like dengue. Why am I reading this? Because it's relevant for our business and we need to be aware of what's going on. This is particularly for modeling infectious disease epidemics. There are SIR, SIER type models, but now what can artificial intelligence do? So we'll kind of muddle through this because there are lots of technical details that, as usual, I'm not going to get into, but I will capture the salient points according to me, subjective, so you have to go and read the paper. So either you are an expert and will find this paper and read it, or you are not an expert but a user like me and you will find some useful information here. That's my justification for doing these sorts of podcasts, because there are some people who complain that I shouldn't be talking about things unless I'm an expert in it. Well, I don't believe in that philosophy. So here we go. Infectious disease threats to individual and public health are numerous, varied, and frequently unexpected, so they can just jump out of nowhere. Artificial intelligence and related technologies, which are already supporting human decision making in economics, medicine, and social science, have the potential to transform the scope and power of infectious disease epidemiology. Here we consider the application to infectious disease modeling of AI systems that combine machine learning, computational statistics, information retrieval, and data science. If you don't know what those are and how they are different, don't worry about it. But essentially, you take the data on disease outcomes from the past and try to use statistics and surveillance information, hospitalization, etc., combined with data science technologies, techniques, and come up with modeling how a disease may spread based on various environmental and human factors. We first outline how recent advances in AI can accelerate breakthroughs in answering key epidemiological questions, and we discuss specific AI methods that can be applied to routinely collected infectious disease surveillance data. Second, we elaborate on the social context of AI for infectious disease epidemiology, including issues such as explainability, safety, accountability, and ethics. So we talked about explainable black box models for AI and interpretable AI models, to say that maybe interpretable models are better in the long run rather than black box models that cannot be directly understood, but then you have another model that explains the results. So let's not get into that here, but just remember that. Finally, we summarize some limitations of AI applications in this field and provide recommendations for how infectious disease epidemiology can harness most effectively current and future developments in AI. That's the broad picture, and let's read few glossaries. Should I read all of it? Not really. Active learning, it's a ML framework, so basically try to minimize a data labeling effort and iteratively asks human user to label relevant samples, and model learns from the replies. So we know how AI tries to do these things. Bayesian optimization is numerically optimizes function that is difficult to optimize or evaluate using conventional approaches. There are priors and posteriors and so on. Causal inference, you know what that means. Explainable AI, again we talked about it, set of methods that that enable human users to comprehend the output created by a black box. We have already talked about this elsewhere, so I'm not going to go more into that. Deep generative models are machine learning models that use deep neural networks, which we talked about elsewhere as well in the first podcast, I think, of this series. Fine tuning, you know what that means. It's kind of a transfer learning, and it's used when data are scarce. So you learn from a region where data is good, and then you try to transfer to cover regions that don't have good coverage. Foundation models, very large deep learning models that are pre-trained on vast general purpose data sets such as large language models. So you just take all the data that's available and train them and then try to apply in specific cases. Graph neural networks, we mentioned as well before, a family of artificial neural networks for processing graph structured data such as social networks and protein structures, which have nodes and links and clusters and so on. Mechanistic epidemics models are models in which a plausible mechanism for the infectious process is represented in an analytical or simulation framework, such as differential or difference equations. So some sort of a advective diffusive model, or some sort of a I don't say first principles like Newton's laws of motion, but some equations which can explain the process in a mechanistic way. Multimodal learning refers to approaches that attempt to leverage multiple types of data such as images and languages. So you mix and match multimedia data you may be getting on infectious diseases in this case. Recurrent neural networks are a family of artificial neural networks designed for processing temporal sequential data. They have been used extensively for problems in speech, natural language, and genetics. I'm ending up reading the whole thing because these are kind of critical concepts. So even if we don't bring it back into the discussion of this paper, they are general terminologies that we all need to be familiar with. As opposed to recurrent learning, we also have reinforcement learning, which is a machine learning paradigm in which an agent learns how to take actions conditioned on its state in an environment so as to maximize a reward signal. Okay, so you have something you are looking at to predict something else, so you want to maximize prediction as a reward signal. With human feedback, these systems can be aligned to match human preferences. In this case, it's about how you respond to, let's say, vaccines or wearing masks and quarantining and so on. So the machine learning is going to try to include the human preferences in this case, which would be location specific, for example. Retrieval augmented generation is a technique to assist LLMs for text generation. So you have some data and then you artificially can generate data based on the data that you have. Self-supervised learning is a machine learning method in which a model learns from data without labels for guidance. So active learning is where you have some guidance as to where it needs to go, whereas in self-supervised learning, it doesn't know. It's like a data-driven model or something that it learns and says, this is what the model is saying, without any input from guidance from humans. Surrogate model or emulation is a model used to approximate another, typically more complex or computationally expensive model. Transfer learning is a process whereby knowledge acquired by a model from an initial task is leveraged for a later task. There are many applications of this terminology. Transformers are neural network architectures that process sequences such as text in parallel and compute the relationships of each part of the sequence to others, enabling an understanding of the context of that sequence. So if you combine large language models and these sorts of things, then you know that we learn grammar, we learn a lot of languages in a very kind of sometimes tedious way, because learning languages is very difficult, especially as you grow older. And you need to know grammar and object, subject, pronouns, this, that, and then context, questions, future tenses, and past tenses, and past participles, so on and so forth. Whereas machine learning can just take everything, many examples, and then tell you what the structure is and how it is being formed without knowing basic grammar rules. Right? Amazing. Zero-shot learning refers to the ability of an AI/ML model to generalize to a new task or problem that is not represented in the dataset used to train the model. So this is just like human beings learning something and doing something else with that knowledge or based on that knowledge and so on. So let's jump to the end of the introduction here. We consider main two main topics in this perspective. So it's a perspective which says where things are and where they need to go and what the drawbacks are and so on, and they will give you some recommendation at the end as well. We might end up having a couple of podcasts at least here. First, we outline how current and anticipated advances in AI can change how we answer key questions in infectious disease modeling. For example, new AI methods can improve the collection and integration of heterogeneous data sources, and AI/ML could be included in policy and decision-making frameworks to improve population health. Second, we discuss some social and ethical contexts of the application of AI to infectious disease epidemiology, and we consider the explainability, safety, and accountability of AI in public health, and provide recommendations for how infectious disease epidemiology can harness developments in AI effectively, which are coming very rapidly at us. So I'm not going to go read the text on the ethical context for AI. That comes up in many discussions overall for AI itself as a technique, plus applications of AI in public health. For example, there are privacy concerns on how you do this. You cannot go sharing people's information, whether it's through AI or directly. Insurance companies will look for it to say, haha, we don't need to pay you, and so on. So you have to be careful about safety and social context and ethical context as well. So AI to answer epidemiological questions. Again, I'm going to read just a little bit of the text. It's a nice long paper with tons of references that you can look up. Okay. One of the key challenges during the early stages of an epidemic is to understand the severity and epidemic potential of the infectious agent, how quickly it will circulate, and what will be the mortality rates and infection rates, the R in the SIR model, and so on. This involves estimating fatality ratios, serial and generation intervals, transmissibility and epidemic growth rates, as well as inferring infection networks and transmission heterogeneity in different settings. So look at the box in a minute. In traditional epidemiology, these questions are often answered using observational data such as case studies, control studies compared to case studies, cohort studies, household surveys, and so on. However, the small scale of such studies and idiosyncrasies of data collection mean that the true transmission process is observed imperfectly and may not be representative of the whole epidemic. The actual chain of infection events and locations where infections occur is often uncertain. For example, individuals may visit multiple locations and contact many people, some of whom might be infectious but asymptomatic, hindering efforts in this process to accurately measure quantities such as the incubation period of the pathogen that you are tracking, or transmission intensity from observational data alone. So how many people get infected by one infected person, for example. Other issues include underreporting, censoring, truncation, non-random data omission, and even data reporting. Here, Bayesian data augmentation has proven valuable in improving parameter inference in the context of missing data, and AI approaches can help in the scalability and inference of such models. So there is very technical term there, Bayesian data augmentation, which I'm not going to get into, so you can follow up if you are an expert or curious. A promising direction involves approximate Bayesian inference, such as that based on variational inference with normalizing flows. Very technical terminology, but we'll jump over it. But let's look at the figure and then come back. There's a table. What did I do with the figure? Here is the figure. I put it way far from where it should be. So let's move it just now. And where am I going to move it? I'm going to move it here. So let's read that and then close this podcast before it gets too long. So the figure is basically showing input, model training, output, and then you have validation steps as well, calibration, and then actions. So that's the general guidance, but there are many panels here. So you have case incidents, and you may have missing data over time, and you have node attributes, so case incidence, population size, healthcare capacity, socio-demographics, which are all together going to decide the transmissibility and other factors connected to a particular infectious disease. And there may be genomic sampling involved as well to see how the virus is evolving, either in response to the medication you are taking or the vaccines you are taking, and so on. You remember all these things from COVID, which we just lived through, so that's how it evolved. And model training, there is several steps involved. This is the graph neural network, the training data, so lots of details that we don't really need. Outputs, of course, over time again, you are going to look at data imputation, anomaly detection, which is not fit into the model that already has been used to produce the output. So validation will tell you that this is an anomaly, and there is a forward detection, forward prediction, which is the main goal of doing this, because when you want to manage infectious diseases, especially epidemic scales, you want to quickly keep trying to see where it's going next, which geographical location, which population, or increased population infections, and so on and so forth. And there are other details, community detection or classification, link, etc. So let's just look at how the actions will be guided. The guide capacity planning ahead of potential outbreaks using past data, be ready, early warning systems kind of approach. Evaluate the effect of public health interventions. If you are doing water sanitation and hygiene, how will that affect the explosion of the epidemic or the transmissibility rates and so on? In this step, you have provide insights into the mechanisms of disease spread, inform resource allocation and targeted intervention. So you want to probably identify the most susceptible population and assign resources there to protect them so they don't become vectors at a very fast rate. And in this step, you have accelerate the development of effective vaccines, enable variant specific targeted interventions. So this is what played out in COVID. So what is A, B, and C then? Let's go back now and look at that with the figure in mind. AI approaches to tackling key epidemiological questions. A, time series analysis using foundation models, pre-training large-scale foundation models with transformer architecture. So some technical details that we will read a bit more in box 1. And in B, modeling infectious disease spread using GNNs. So again, A and B. Okay, so A was time series analysis. So we use all the Bayesian data augmenting and all these good things, and modeling infectious disease with GN and pathogen dissemination. So many details there. Under C, jumping ahead, we have predicting immune escape mutations using biologically informed deep learning models. So essentially multiple steps where AI is involved in every step, from input model training to output, and then B was modeling infectious disease spread using. So you want to understand the disease and what it's doing in terms of its relation to people, density, interventions, maybe environmental factors, and so on. And then you want to start modeling it and to make sure you are able to detect the infections at community levels and nodes, which are obviously depend on population size, healthcare capacity, and socio-demographics, and so on and so forth. So you get the idea, right? So let's go back now here and look at this normalizing flows. So some more technical things we'll read a bit more before going to prediction and forecasting. Remember, I'm chopping the text and reading just some main points. This reframes the problem from one of sampling to optimization, which can be addressed efficiently using gradient-based deep learning techniques. Again, some technical terms, but essentially you will never have enough data. So if you go after sampling size, saying it's not enough, you will never make progress. So optimization is aided greatly by AIML as opposed to what we used to do before, saying statistical analysis is done, but sample size is an issue, and so on and so forth. Given the difficulties in generating a complete description of the transmission tree that underlies an epidemic, model-based analysis are performed on routinely collected aggregated data such as counts of cases, hospitalizations, or deaths. Mechanistic and semi-mechanistic disease transmission models are commonly used to test hypotheses and estimate key epidemiological parameters such as transmissibility and virulence, that's infectiousness, let's say, with associated uncertainties, which is always the case. Although these models provide substantial mechanistic insights into transmission and can be used to construct counterfactual scenarios, they often come with considerable computational costs due to the complexity of the numerical methods and inference in a high-dimensional parameter spaces. Okay, again, technical terms, but counterfactual is basically where you have a certain situation you have arrived at. You can go back and integrate to see if people didn't travel so much, what would have happened? If vaccines were given, what would have happened? If hygiene was better, what would have happened? So you create counterfactual worlds where actions could have been used to make things better, ameliorate or mitigate the infections and epidemic spread, and so on and so forth. Okay. Should I read more? We'll read table 1 and box 1. Improvements in the speed of model computation offers additional opportunities to increase the model complexity and realism, including potential linkages between individual transmission heterogeneity and population level outcomes. So you are looking at agents which are running around individual human beings or family units, and then you have population level. So when you say in the contagion has become community level, which means it's not jumping individual to individual, now it's just jumping from groups to groups, or it's enough infected people that it can just keep spreading, right? That's population level outcome. As AI accelerated methods have the potential to reduce model run times from weeks to hours, they could substantially speed up the iterative process of informing policy decisions and model refinement. So we'll come back and look at table 1 for that, which I have again placed after the figure here. So we'll come back and do that in the next podcast because it's a nice transition to prediction and forecasting. Okay, so see you in the next part of this topic. Okay, so let me stop this. How long? I'm only 22 minutes, so it's okay.